Okay, so we are recording now. So we're picking up from the previous lecture, and we were training a linear regression model, very simple one written entirely in PyTorch using the wine quality dataset. All right, so I'm going to go ahead now and hit train. We've described all of this, including MSE, and we're going to let it train for a little bit. Then we have to obviously evaluate that model on the test set. All right, so that's going to be the next part. And we're going to need to have some metric to use, which is usually going to be R squared, right? So R squared is actually a very picky metric. I've had lots of problems with it over the years because it likes large data. It actually, when the model didn't learn well, it gives like negative values, which it shouldn't give. If you go to a stats course somewhere, people will tell you that R square is always between 0 and 1. Obviously, that's not true because it can return negative, but it just means that when you get negative, there's a dysfunction in the in the equation. Okay? So you definitely do not want negative, but it can give you negative. It's just really bad. All right, so we want a model that's pretty stable. So we're going to look at that. But R square can be a little bit tricky. All right, so we should be, we're running, I think only 100 iterations, so keep that in mind. Maybe if we did more iterations, the model would be better. But anyway, at least I'm going to be consistent in my analysis. So I think it finished. So I've done the training. Now I'm going to proceed to evaluate this regression model. So evaluate it, I'm going to need the test set. So I'm going to go ahead. And if you notice, all I do is I grab X test TR, right? You remember from the split. I run it through the model and it gives me Y-pred test. Do you guys see that? Y-pred test, if I print the shape, it's a tensor dot shape, and it's 980 by 1, right? So that's essentially the size that I had. So now I need to evaluate it. And that's going to be by using this function. So from sklearn, I'm bringing in the R squared. Okay, here we are. So notice one thing that's key here. I'm using this function R squared. I'm going to change it a little bit just to show you how it works. Notice that you provide to it. So you provide to it the real data, which is going to be Y test TR, right? That's the real data. And we provide the predicted data, which is Y-pred test. Got it? So both of these are 980 by 1. Notice that I also do this, which essentially to NumPy, just as it implies, I'm converting from a torch tensor to a NumPy array. And then the other thing that I do that you'll do sometimes is you have to detach things from the computational graph. So this is actually a nice error because whenever you forget and you get this error, it says you need it to detach. So you have to do dot detach, and that's just something that's necessary so it's no longer connected to the computational graph. Make sense? All right. Also, another thing is that the real data needs to go before the predicted data. That's just the way that this equation works. But I have noticed if you invert them, it can give you a different value, possibly a lower R squared. So you don't want that. To be on the safe side, so the last value should be the predicted value. So I'm going to make it look like I had it before. So real data goes first, followed by predicted data. Okay? And like that. Got it? All right, so now that I run this, I'm going to print the R squared, and you can see I get an R square of 0.24. It's not zero, but it's not negative, which is something I hate to get negatives. Um, but it's not great either. Now, there are some regression models that you can definitely get like 0.90, 0.98. You can. That's definitely, and that's a great situation. I'm happy for you if you get that. In your homework assignment, once again, that I'm going to give you, remember, I'm going to ask you to find a regression data set and a classification data set. So I'll be looking for this R squared. If you pick a good one, it might give you a really high R squared. If you want something more challenging, right? You can expect lower R squares. It's fine by me. Just don't get a zero, right? So, but if you get something like this, that's perfectly fine. It just might mean that the data is too noisy. Also, you might not be using a good enough architecture. You will have to run it through XGBoost, as XGBoost is usually better. So we'll see that today. I mean, we'll try it out. But anyway, that's the whole pipeline. Are there any questions on this one? No? Makes sense? All right. So we did the R squared. So I could print these, but obviously, we can just see that they are, in fact, 980 by 1. There's 900 of them. One thing I do sometimes, especially with regression values, is I just print them. And you'll understand why. So this code just iterates through all the samples in X-test-TR and predicts the Y-test and compares it to the real. But we actually look at it. And there's some value in this. So what this is saying is, oh wow. So it is obviously tedious if you have a lot of samples, but what I'm doing here is I'm showing the predicted versus the real. So the way to interpret this is, okay, for this vector, the rating was 5. My model predicted 5.9. Well, that's not bad, actually. For this example, it was 8 and mine predicted 6.4. Okay, so a little bit worse. This one was 6 and it predicted 6.5. That's good. For 7, it predicted 6.5. For 4, it predicted 5. For 4, it predicted 4.9. For 5, it predicted 5.7, and you get the idea, right? So you obviously the R square is one quick way with one metric to evaluate the whole model, but there's nothing wrong with looking at these values, especially if it's 1,000 and you're really invested in this project. It's well worth looking at every single one. And it gives you a sense of how the model is performing. Does that make sense, guys? Now, keep in mind here, maybe rounding would have been something, there's different things that you can consider. But in any case, that is this approach. Because this is going to be a little bit annoying. I'm going to remove this part, but I wanted to demo it at least one time. Okay? Any questions on this? All right. So I'm going to remove this one. And now let's move on to the code. So obviously, we're going to have to repeat this process for all the different architectures and compare. There's one thing I do want to do. If you notice, if I was running this Jupyter every time, then it would be a good idea to change this random seed to a fixed value, because you're going to be comparing. If you were running it every time you have a different architecture, then you want to make sure you're using the same train test split. In this case, I don't think I will be rerunning it every time, so we can leave it as is for now. All right, so now let's take a look at the next step. So once we do this evaluation, printing all these values here. Okay. So the next thing that I want to show you before we start repeating the process is I want to show you deployment. Deployment is actually quite easy, right, with Onyx. And so I'm going to take this opportunity to do that now. So we've already loaded the libraries, which is torch.onyx. So all we have, and there's several ways, by the way, of deploying an Onyx model. So there's like 3 different ways that we could do this, but this is just one example. So usually I just use this code. And the only trick is that you have to look at the version that you want out that's going to be compatible with the HTML code that you're going to be using later. So remember, deployment means what? Putting it on the web, right? So how are you going to interact with that model on the web? The easiest solution is probably what? HTML and JavaScript, right? Which is something that most people are going to be familiar with. Does that make sense? But if you're doing that, then you kind of have to make sure that a version that you're using here matches the version of JavaScript that you're using over there. Okay, that's it. So I will come back to that later, but for now, I just want to show you a very simple way of deploying the model. So what do we do to deploy an Onyx model? We set it to eval. So we take the model. So currently the model is in training mode because I just trained it, right? If I want to evaluate it, I want to switch it to eval mode. So I probably should have done that here when I was evaluating the model. I should have done eval mode. But yeah, you set it to eval mode, and then you just export it like this, torch.onyx.export, where you specify a few parameters. The first one obviously is the model itself. So you're exporting that model. But then you also want to define what name you're going to give it. So in this case, I'm calling it dlnet winedata.onyx. So that's going to be the name of the file that is created. Do you guys understand? And that's the file that you will upload to the website. Additionally, you need to provide a dummy input, which is essentially to tell it, okay, the input vector that goes into the model is of this size. Okay, so in this case, here it is. Dummy input is equal to torch.rand 1, 11. Why 1, 11? Because 1 is one batch, or batch of 1, and 11 is the number of features. Got it? So when you guys do your homework, let's say that your data set has 42 variables. When you deploy 1, 42. Got it? That's like the one thing you have to change. You don't even need to care so much about the output because that's going to be consistent. All right. And then you can define a few input names, input and output names, such as input 1 and output 1. And that's it. So if this is correct, we run this right now with no errors. You see, we got a green check, and now you have a model that has been created. So DLNet wine data Onyx. So I assume this is in the drive. So let's go over here. My drive, and let me know if you guys see it. So there should be a wine. No Onyx. Oh, no, here it is. Right there it is. Do you guys see it? So I'm assuming then you click something like download, maybe. Yeah, download, and there you go. That's it. That's now you have the capability to train models with machine learning regression or classification at this stage. And then you grab that model, so you guys saw that I created it. So then you go over here, export it as an ONNX model by following those parameters that I mentioned, and that's it, you're done. Now you can take that model and use it for inference. You can't train it in the web anymore, right? So you want to come back here to train it, but now you can use it for inference. So give it vectors of 11, and it'll give you that wine quality. Any questions? All right, so for your homework assignment, you will have to do this. For your classification and your regression, you will need to go to GitHub Pages, create an HTML and JavaScript page, which will obviously be made up of some text boxes for the inputs, buttons, things like that. Those inputs will go into the model will predict, and then you will display the result. Got it? All right. So I'll cover that phase in the next class, in next week, but at least for now, you know how to export your ONNX models, okay? So you have it available, and then next week I'll spend 30 minutes or so, that's how long it takes, just to go over how to link it to a website with HTML and JavaScript, and I have plenty of examples on my GitHub that you guys can just reference also. All right, some students in the past have even done images. I had students that did sign language with a camera, so they would do this and that, and the thing would say what letter it was. So there's lots of things you can do, and there's many examples. But anyway, let's move on. All right, so we've done the ONNX export part. So now the model has been made available. The last part of this, before we go back to all the other architectures, is I want to talk about XGBoost, right? So, there's so many times that there's a problem, a regression problem, you go in and you try all kinds of neural network architectures, and then you're just like, what about XGBoost? And then you run it with XGBoost, and it's always better. Now, XGBoost has limits. XGBoost is good for interpolating. So XGBoost, what that means is if the values are within the ranges of what it got in the data, then it does a really good job. But XGBoost is not great at extrapolating. And extrapolating means what? I've seen a lot of values within this range. Let's say that I saw a whole bunch of humans with ages between 4 and 99. So in that case, I'm really good. Whenever I get a human that's between 4 and 99, I'm really good at predicting. But extrapolating means, what if I get a human that's 103? That's not in my data set. So XGBoost is not as good there. And in that case, neural networks actually can become very handy because neural networks can extrapolate really well. Do you see what I'm saying? So if I get cases so it's like an if statement. If the human is between 4 and 99, XGBoost will probably do better, use XGBoost. If the human is outside those ranges, we need to extrapolate, so a neural network likely will be at least accurate. All right? So anyway, so that's kind of the difference there. Remember, as I said, XGBoost is not a neural network at all, but for the last 10 years or however long, it's always been the best model when dealing with these types of small regression-based tabular data. Okay? You go to Kaggle right now, look for competitions related to regression, tabular data, and you will see XGBoost always wins. Okay? So at some point, maybe later in the semester, I'll come back to how XGBoost works, but it is a tree-based network, right? So this is where the features become nodes in a tree. So it's like acidity. well, if acidity less than 2, then I go this way. If acidity greater than 2, I go this way. You see that? That's a tree. Like if you remember your depth first search, breadth first search, right? DFS type of tree traversal. So it's that kind of a problem. But the machine learning is deciding how to pick things based on going in different branches of the tree. And it's called XGBoost because although it's based on an algorithm based on trees, it's got a whole bunch of optimizations. In fact, if you notice, the library that we were using is a specialized library, not coming from sklearn or NumPy or anywhere like that. It was its own thing. So it's in fact really fast also, very efficiently made and so on. And you can deploy it via Onyx as well. So that's also a really nice feature. All right, so now let's try XGBoost, see what happens. So I usually don't remember what the results are with these, but in my experience, XGBoost has been better with a lot of data sets, and on Kaggle, it also is. So here I'm just going to use default settings as I don't want to spend too much time on it. I just want to highlight this one. So xgb.xgb regressor, the number of estimators is 100, and some other default parameters like a maximum depth of the trees, etc. So we instantiate this object, regressor. And then notice here, we're just going to train it with X train and Y train. Okay. Any questions? So I'm going to do regressor.fit. That's how it works. And there it is. And now that I'm going to do this, I've trained it. So now I'm just going to predict on X test, right? So I have X train, Y train for training. Now X test, Y test for testing, right? So I run on the train model, X test, and I create my Y preds. If you notice, the training was quite impressive, right? How quickly it was. So that was pretty nice. The shape should be 980, same as before. 980, okay. Here are the values, and now we need the R squared. So we give it Y test and Y pred, right? Just like before on R square. And we have an R square at 40. Do you guys see that? What was our previous R square? 0.24. So this is definitely a significant improvement, without a doubt. Okay. So my suggestion, at least where we are today, AI is always changing. And, at some point there's like a XGBoost NN and, it's better. So who knows? But for now, this is in regression and tabular data, especially because it's so small, right? And neural networks benefit from massive amounts of data. So that could be one of the reasons why it always does so well. But with small data sets, regression, Excel type things, it does really well. So it's definitely something in your arsenal, right? Always use it. Got it? So we've benchmarked our data, wine quality, on a linear regression, a very simple, and XGBoost. So I almost want to say that I have a range right now from 0.24 to 0.40. I bet one or two of the better neural networks will be maybe at 0.30. We'll see. Yeah. So I do have an architecture called a residual network that does well. So I haven't tested it against XGBoost, but I do think that one's pretty good as a neural net. All right, so let's go back to our Jupyter notebook. And as you can see, we've finished, with XGBoost. The next step would be to deploy it. I'm going to skip this part for today, but on the homework, I may assign this as well. So as a reference, this is where you need to look, okay? But I will provide plenty of examples so to do this, but it's going to be pretty similar, right? There's going to be some, to deploy the model, some input that you define, some libraries to save it, and there's several approaches to doing this. Okay, but this is just some code on how to deploy the model and use it. And that's it. So that's the conclusion for this Jupyter notebook. So now we can just try the other three architectures and see how it performs. Is this clear, guys? Are there any questions? So on your homework assignment, I haven't created it yet, but it'll be a classification, a regression model. You will use neural nets, XGBoost, and you will deploy the models and run them from the web. All right, so now let's go ahead and go back to the architectures, which were defined around here. Yeah, linear regression. And we're going to try a different architecture. So in this case, I'm going to use, instead of linear regression, just a slightly more complex neural net architecture. So we're going to go back up. Back up here. Yeah, so that's why I removed it. All right, so the next architecture that we're going to explore, so the first one was linear regression. If you remember, just one input layer and one output neuron. Now I'm going to try an MLP for regression. So I'm going to take this one, and this is going to be my new architecture. So we're going to look at the graph and how this looks, and we're going to try to implement it. So here we are, same approach. This is an MLP net. It inherits NN module. It's got the same two functions, init and forward. Notice that now, because it's a because it's a multi-layer perceptron, it'll have one input layer, one hidden layer, and one output layer. So it's the init constructor, still the same thing. We standardize X means and X deviations. We do the super init. We inherit the class, same thing as before. We save our X means and X deviations, and then we just create what we're going to use. So this will be a neural network. As you can see, it's got an activation function, which is sigmoid. So now we're going to go from 11 to 8, and then 8 to 1. And that's it. That's it. So here is the architecture. So in the forward, you get X minus X means divided by X deviations, standardizes the data. So now X goes into linear 1, which is from 11 to 8. Then X goes through the activation function, which is a sigmoid. Remember, just maps it from 0 to 1, right? Then we have a dropout, which is something I haven't discussed yet, but just another type of processing. And then it goes into linear 2, where linear 2 goes from 8 to 1. And we're predicting still just one neuron, and that gives you Y-pred. Do you guys see that? So now let's look at this as graphically. I'm going to open up the whiteboard here. Okay, so this regression, this is an MLP. It's an MLP. So it's got, for contrast, the linear regression one was only like this, right? 11. This was the lin regression net. So lin reg net. Now the MLP that we're doing still has the same input vector of 11, right? But now we're going to move this out a little. Still just 1. This is the output. This is the input. But this one has 1 hidden layer in between. How many neurons did this one have? It was from 11 to what? To 8, right? And this would be called, of course, hidden 1. So there you are. So 11 to 8 and 8 to 1. Remember, there's a weight matrix here, 1 over here, right? And that's essentially how it works. Any questions? Pretty simple. One last thing I'm missing. Remember, there is no activation function here. There was one activation function here, right? All these values are passed through a what? A sigmoid that will map those values into a range between 0 and 1. And remember, that's what provides the nonlinearities, the ability to not just be linear model. Okay? All right, so I'm not hearing any questions, so now we can proceed to try this architecture. Okay, so we should be back to our Jupyter Notebook. So we have a new architecture. It's called MLNet, or MLPNet, sorry. So we added train function, same thing. Notice here, we're going to change this to MLPNet. MLPNet. Otherwise, everything is the same. That's another nice feature of this approach. You can try different architectures without having to change the rest of the code. Model is now going to be MLPNet, which is going to be mapped to the optimizer, still the MSE loss, and we do the training. So now I proceed, I start the training. Remember, the objective is for this value to go down. Usually in the very beginning is where most of the improvement happens. Right, so it's only doing about 100 iterations. Okay, so it's finished. Now let's run these. And we evaluate. 0.26. So I went up slightly, right? Do you guys see that? So yeah, so this is the nature of this. Now let's try the next architecture. Again, keep in mind, it may need more iterations. The neural network just has a lot more parameters that you have to play with. Okay, so the next one is going to be DLNet. Okay. So at this point, hopefully, this is starting to be very repetitive, right? So to the point that you kind of get it, right? So I'll just now more quickly move through these, right? Because I assume you guys get it. So this is a DLNet of 2 hidden layers. Same idea here. Notice the architecture goes from 11 to 10, 10 to 6, 6 to 1. Okay, so So it goes 11 to 10, 11, 10, 6, 1. So if we draw this out, we're going to move to a new page. So now the architecture is 11, 10, 6, and still 1. Do you see that? So you have 1, 2, 3, 4, 5, 6 neurons, and this one all the way to 10. And these, of course, are your inputs that are coming into the model. But that's essentially what we're building, and this is how it works. At this point, this is a deep neural network because it has at least 2 layers. All right, so we're going to try this one. Obviously, this is going to start to take a bit longer because it's a deeper architecture. But it should be ready to go. It's just called DLNet. So I'm going to run it. There we are. Have the training loop. And I need to change this now to be DLNet. Got it? That's it. That's the only change. Everything else should work. And we start the training. Okay. Notice this loss it went from 0.61 to 0.22. So it's a little bit different from the MLP and how it was behaving. But it's not great, right? So you would always want it to go down. This kind of goes up, down. All right, it finished. So now let's try these. 0.35. That's a nice improvement, right? Nice improvement, I should say. Is it better than XGBoost? No. Which is, as I said, this is a very common thing that you see when you're doing these types of things. So that you can see now why I included XGBoost as an exception here, where something does better than neural nets. But this DLNet did do nicely, 0.35. Any questions, guys? No questions? All right, so now we're going to do one more. This one is kind of interesting because this takes the idea of architecture and we're going to like expand on it. So let's go here and create a new cell. And I'm going to create a new architecture. This one. And this is a fun idea, actually, that I think ties a lot to the concept of residuals, which you hear me say a lot, right? Residuals, this, residuals, that. We will do at least two, a residual neural net like these, and then a residual neural net for images. So we'll talk about that. But this is kind of like that idea. So the idea with residuals, if you remember, was that we would have this, and this is just a normal neural net, right? Oops. X goes into the function, that's the model, and you produce Y. I made this all kids. Right? But the problem with this, with a neural network that's very deep, is that you would have this idea of the vanishing gradients, the weights become 0. So a solution to this was to do that, right? So you take the original input plus a little modification to it, and then you produce Y. And you keep doing that, right? So we're going to do something similar, right, in our next neural network, which is something called a linear plus nonlinear. So essentially, what we're saying is, okay, we tried the linear regression model, and then we tried an MLP. Do you see what I'm saying? What if we tried both together somehow? Do you see that? Let's run our X through the linear and our X through the nonlinear, but we combine them together in some way, and that combination also influences the weights, right? So what would happen then? So this is called a linear plus nonlinear model. All right, so how does it work? And actually, I like this example because this is one of those that expands your mind, right? As to what the many things that you can do with architecture. So here, essentially, it's combining this one, a linear, and an MLP into a single model in the architecture. So notice how we are going to approach it. So I have linear plus nonlinear, I'm going to denote the linear part as F1 and the nonlinear part MLP as F2. So notice I'm calling it linear plus nonlinear net. It inherits NN module. It still has the two functions, the constructor in it, and it also has the forward function, okay? So all that's going to happen here now, if you notice, everything's the same, but I'm going to have two sections for it, F1 and F2. And they're like two separate nets. They start with X, and they just follow the architecture until they produce a value. So if you notice here, linear F1, I'm calling it F1 linear 1. All it does is it has an NN linear from 11 to 1. You agree that that's the linear regression model, correct? Okay. Then F2 is the MLP architecture. It's going to go, notice, from 11 again. So that implies that X goes into this, but also into this, right? Just kind of how we did the heads, maybe. Remember the heads, how we had X went into one head, then another head? It's something similar. So here, it starts at 11, but now it goes from 11 to 14, 14 to 1. So I have F1 and F2. Okay, now that I declared them, then the next step is, I standardize it. And then notice here, X goes in to F1 linear to produce F1. Okay, then X goes into F2 linear, right? Goes through the activation, goes to the next layer to produce F2. And now all I do is I combine them to predict Y pred. Do you see that? So F1 plus F2. What's important to note or notice about this architecture is, remember, we're building it like this, but the weights of both this architecture and this architecture are being updated, right, during training. So sometimes the linear might be better, sometimes the nonlinear might be better. So the concept here is, what if a linear actually works really well here, but sometimes it fails? And so just some of the time we need nonlinear. So then if you think about that in terms of the weights, it means these weights get most of the changes, and then you just have a slight change here for when you need it, for some special cases. Do you see that? So that's the beauty with this approach, is that the weights are going to be changed because we're considering both. So that's why it's called linear plus nonlinear. Does this make sense, guys? Are there any questions on this one? All right, so yeah, but that's the intuition. So that maybe a linear was enough, and so F1 is enough, but sometimes we also have F2 just in case to help out a little bit more. Now, it's not guaranteed that it's going to work here very well, but let's see how it does. So we already had a good performance, I think, with the DLNet. So I'm going to copy this. All right, and now I'm going to run it. All right, so that ran. Train loop is the same. Now I'm going to change this to be linear plus nonlinear net. All right. Oh, error. Okay, so there must be a typo in here. Let's correct it. So it says this should be linear one. Right? Yeah, so that was missing. All right, so run it. Run it. There we go. So now it's training. So let's see what happens. So far we had 0.24, 0.26, 0.35, and XGBoost at 0.40. XGBoost at 0.40. Now, because of the fact that XGBoost is great at interpolation, but not good at extrapolation, then what you could build if you're building an application here is to take the XGBoost model plus the best performing of the neural net models and use them together to do your predictions. So let's see what happens. All right, so it finished training the linear plus nonlinear. Now let's see, 29. So not better than the DLNet, but now keep in mind, the great thing about this is what if I decide instead of so if you notice here, I use an MLP, right? So what if I use instead of an MLP, a DLNet here? Do you see that? So that's going to be the last case. We're going to build this one. You guys can help me out. Let's think it through. All right. But so far, the best performing was that DLNet at 0.35. So now let's create linear plus nonlinear, right? Almost everything is correct, but we just have to change this part. So let's look at the architecture of DLNet. That's this one here. So it goes from 11 to 10, 10 to 6, 6 to 1. All right, so that's what we want to create here. So I'm going to do 11 to 10. Okay. Control V, right? So this is going to be F2 linear 2, activation 2, and this is 10 to what? 6, right? Do you guys agree? 6? Okay. Also, this sigmoid, what did we use in the DLNet? We use ReLU, right? So I'm going to use ReLU here. I'm going to use ReLU instead of sigmoid. Do you see that? The ReLU is considered to be better for neural networks. All right, so I've done 11 to 10, 10 to 6. I probably need one more here. We're going to call this one linear 3, activation 3. And this one is what? What's this value here? Huh? 6? 6? All right. Oh, is this 6 to 1? So 11 to 10, 11 to 10, 10 to 6, 6 to 1. Very good. So then actually this last one here. So we can get rid of that. Do you all agree? All right. So now we've declared these. So now let's create the actual architecture in the inference function. So F2, X goes into linear 1, goes into activation 1. Okay, so then linear 2, correct? And activation 2. But let's see. I have this a little bit different. All right, so X goes here. X goes, I don't know why. Okay, yeah, I get it now. So F2, right? F2, linear 2, F2, and then linear 3 activation. Oh, here, do we need this? No, right? Okay, so let's get rid of it. Do you guys see that? You don't need a ReLU activation because this is the last one at 6 to 1. So we don't need to map that to anything. So this is where in classification, we would have used softmax. But here in regression, we don't need to do anything. Got it? So that was my mistake. Any questions? All right, so now let's finish it. So linear 1, activation 1, linear 2, activation 2, and then finally linear 3. This one, linear 3 to F2, and that's it. So this should be correct. Yeah, got it. So in this example, we've implemented a neural net, a deep neural net with ReLU activations to see if we can get better than that 0.35. Okay, so let's try it out. Okay, we ran that. Training loop. Linear plus nonlinear. And it's training. So linear, yeah, plus nonlinear net. So let's see what happens. Point 24. This actually looks nice. The losses are nice, right? So this is how I want to see these losses, but I always get depressed when I get this. It's tracking so nicely, and but this is very common in these types of neural networks. I don't know if you noticed as you're training your LLM that it beautifully always goes down. There's something about transformers and GPTs that loss just always tracks really nicely. But yeah, here you can see it did this. So one other thing I'm gonna do is I'm gonna cheat a little, and I'm just gonna give this, since there's more things to learn, I'm gonna increase the number of epochs. Okay, so I'm gonna say n epochs. We're just gonna give it what, like, we've already established that these architectures are good. What was it, 100, right? So let's give it 400 epochs. Let's start from a fresh copy. Let's see if this gets better. If not, that'll be it. But we did cover a lot today, I think, right? So we cover a lot with regression. Okay, so far again, 1.19, 0.85, 0.40, 0.42, 0.44, 0.38. So it's tracking nicely, right? So this is desirable behavior. 0.59. So this, when you run into these kinds of things, this is where you start to want to try things like batch normalization, dropouts, all these other techniques that are there to somehow smooth things out a little. It's going back and forth to 0.40, 0.50. 0.36, good, so back on track. So while we're waiting, do you guys have any questions? No? Yeah, so let's let it finish. We'll conclude with this today. So what I have left is to do the classification version of this. We'll do this in the next class. It should only take us like that first half. So we're going to start again next class with wine quality, but now manipulate the data to make it into a classification problem. It's going to be a highly imbalanced data set, so that's going to be very interesting. And we're going to deal with that. And probably we'll cover cross entropy also next week. So that's kind of the plan, just to kind of finish up some of these topics. I remind you that your LLM's homework is due a week from today, and everyone needs to present up here a model that can answer questions. Okay. So that homework, and be on the lookout for homework number 3, which I will be posting sometime this weekend, but you already know what it is. Find a regression classification data set, train it, all the statistics, and deploy it. Okay, and that'll be homework 3. All right, so I think it finished. Yeah, it finished. So let's look at the performance. We gave it a lot of computing power, a stable architecture, a lot of training, 31. So not quite there, but encouraging, right? This is the kind of thing that, while it doesn't get you that 0.36 that you were looking for, it is encouraging somehow. All right. Does this make sense, guys? All right. So this is probably the easiest topic that we can cover, right? Regression type problems, but that doesn't mean they're not very interesting and very useful. All right. So the next class, as I said, we'll move on to classification and cross entropy and continue from there. All right. So I'll end the video here. And if you guys have any questions,